Welcome back. Well, I'm now going to prove to you that the centripetal or the magnitude of the centripetal acceleration is equal to the magnitude of the velocity of when you're going around a circle divided the velocity squared divided by the radius. So let's start with the drawing just so that we know what we're doing. Just as much for me as it is for you. So that's the circle, and as you can guess, that's going to be our path. And let's call P our position vector. And let's see, this is the center of the circle right here. We do the position vector in magenta. So let's say that this is P, my position vector. Let me draw that bolder. Let me do it. Here you go. So that's the vector P. That's the vector P. And let me define a few other things over here. So let's say that the angle that it's forming with the positive x-axis, let's say this is the positive x-axis, is theta. That says theta right there. And let's say the radius of the circle is r. So what we do, we have a object. It's right here. This is its position, right? Defined by this position vector, and it's spinning around. So its position vectors going to, at some point the arrow is going to be pointed like there, then like there. It's just going to be going around and around a circle. But this is its position vector at some moment in time. So what is that position vector in our kind of what did I call that? Our bracket notation of vectors. Well, we have to figure out its x and y component. So its x component is right here. Or you could almost say it's its I component. If we were doing the engineering notation, that's its x component, and that's its y component, right? So in our bracket notation, or whatever, I always forget what I call things, P is this. P, which is our position vector. What's its x component? It's the radius times the cosine of theta. This should be second nature to you at this point. Radius times cosine of theta. And what's its y component? It's this, right? It's just this. That's its y component. It's radius times the sine of theta. Fair enough. Hopefully that makes sense to you so far. I just defined its position vector, and I drew it out here visually, and then I also wrote it analytically in kind of its x and y components, as a sum of its x and y components. Well, that's good and everything. So let's see if we can figure out what its velocity vector is. Well, what is velocity? Velocity is actually just a change in position. And actually now we are actually dealing with velocity, not speed. We will actually get a vector. So what is the velocity vector? So the velocity vector is going to be, at any given point, in a different color. The velocity vector is going to be tangent to the circle. It's going to look something like that. That's going to be the velocity vector. So the velocity vector is equal to the change in the position over time, right? So let's take the derivative of the position vector with respect to time. And how do we take a derivative? Well, we could just take the derivative of the x and y component separately, and I'll show you how we do it in this notation. And if you think about it, it should make a little bit of sense. So the radius is constant, right? As we go around the circle, the radius isn't changing. And another thing to keep in mind, we're spinning around the circle at a constant rate. So my speed isn't changing. My velocity is obviously changing because the direction is changing. But the actual rate at which I'm spinning, or the angular velocity, is going to be a constant. That's something to keep in mind for what we get to in the next step. But anyway, let's take the derivative. So let's take the derivative of the x term first. The x term. Well, r is just a constant, right? So it doesn't change. We can just take the r out. And then what's the derivative of cosine theta with respect to time? Not with respect to theta. Remember, we're taking the derivative with respect to time. So we do the chain rule. It's the derivative of theta with respect to time. So it's the derivative of theta with respect to time times the derivative of cos of this term with respect to theta. And what's the derivative of this? Well, it's minus sine of theta times, let me put the minus out here, minus sine of theta. I just didn't want to put the minus right in front of the sine because you would think it's a minus sine theta. So it's minus r times the rate of change of the angle with respect to time times sine of theta, right? The rate at which this term is changing with respect to theta. Let's do the same thing on the y side. R is a constant. Chain rule. the rate at which theta is changing with respect to time. Theta with respect to time. And then what's the derivative of sine of theta with respect to theta? Well, that's cosine of theta. Right? This was just the chain rule that I did. So let's see if we can simplify that a little bit. So d theta dt in both of these, that's the same thing as angular velocity. And watch the video on angular velocity if that doesn't make sense to you. But we can simplify this as just w, right? Angular velocity, and that's going to be a constant. And we have an r there. So let's see, we have, let's take a wr out of both sides. So we have the velocity vector is equal to, and this was an equal, the velocity vector is equal to wr. Actually, let's take a minus wr out. So minus wr, and then this term is sine of theta. Sine of theta. And we're taking a minus wr. So the wr goes away, and then we introduce a minus sign here. So it's minus cosine of theta. Minus cosine of theta. Good enough. And the reason why we were able to take, and this w, remember, is going to be a constant. It's not changing with respect to time. The angle is changing with respect to time, but not the rate of change of the angle. It's spinning at a constant rate. So what's the acceleration vector going to be? Well, the acceleration vector, and I'll switch colors again to keep it interesting. The acceleration vector is just the derivative of the velocity vector with respect to time. So it's the derivative of the velocity vector with respect to time. And that equals, well, let's take this is this constant term, so let's leave it on the outside, minus wr. And chain rule again. What's the, if we're taking the derivative with respect to time, first we have to take the derivative of theta with respect to time, and we don't know what that is. That's just going to be w, d theta dt, and then times this expression, the derivative of this expression with respect to theta. So sine of theta, the derivative is cosine of theta. And then on the y side, we have, well, what's the derivative of theta with respect to time? Well, that's just, that's going to just be omega. And then what's the derivative of minus cosine theta with respect to theta? Well, that's sine theta. And once again, this is w, and this is w. And we could take the w out of the equation, and we get the acceleration vector is equal to, take the w out of the x and y components, is equal to minus w squared r times cosine theta sine theta. Or we could take this r and multiply it times both of these, the x and y components, and we have the acceleration vector is equal to minus w squared r cosine theta r sine theta. Now, does this thing here look familiar? Well, sure, that was our original position vector. So we could say that the acceleration vector is equal to minus our angular velocity squared times the position vector. And that makes actually a lot of sense, because, well, w squared is going to be a positive term. And what it's saying is it's going to be the negative, the direction of this vector is going to be the negative of the direction of the position vector. So if our position vector is going outward, our acceleration vector, which I'll draw in green, is going to be going inward. The acceleration vector is going to be inward. So it is what we wanted to see. And let's see if we can express this as a function of the magnitudes. So this will also say that the magnitude of the acceleration vector, and that's just a without a arrow on top, I could have put brackets around it, is equal to the negative angular velocity squared times the magnitude of the position vector. And what's the magnitude of this position vector? How long is it? Well, its magnitude is r, right? By definition, not in the beginning of the thing. So this is just r. So acceleration is equal to the negative angular velocity squared times r. And what's angular velocity? Well, we learned in that video that angular velocity, I'll do it right here, is equal to v over r. If we just talk about the magnitudes, not the vectors. Remember, if we're not drawing an arrow on top of these variables, they're just scalar quantities. So the acceleration is equal to, and actually we can get rid of the negative sign because we're not worried about direction right now. But we could keep it there. Well, it doesn't matter. So what do we get? We get v squared, because the magnitude of this, its absolute value is essentially magnitude. So you get v squared over r squared times r. So r times r squared, you get the acceleration is v squared over r. And that's what we set out to prove, and I'm out of time now. So I'll see you in the next video. Hopefully I didn't confuse you.